Penny's wager is a neat example of a game with some surprising counterintuitive properties. It's easy to analyze from a Markov chain perspective. It involves flipping a coin, and it happens to be named after a guy named Penny. And it works like this. You have two players that are flipping a coin, and they're recording the last three flips. Right, so they flip it a bunch of times, and they keep track of the last three things that they have seen, and they are betting on which three tuple is going to arrive first. So they're looking at the last three things that have happened, and so there's 8 possibilities in total, right? You could have heads, heads, heads. Heads, heads, heads. You could have tails, tails, tails. You could have heads, tails, heads. Easy to see. There's 8 possible examples of that, okay? 8 things that could happen. Now, player 1 is sitting there waiting for this sequence to occur. Heads, tails, tails. And player 2 is waiting for heads, heads, tails. And the winner is whoever sees their sequence arrive first. So let's do an example here. So let's say they start off, and let's say that what you see is first it's a tails, and then let's say it's another tails, and then it's a heads, and then it's a tails, and then it's a heads, and then it's a heads and a tails. And once that last tails happens, you'll notice that you've got heads, heads, tails, and therefore player 2 wins. Okay, player 2 wins. And then, the game would be over. And you can look back here and verify that at no point in this tiny sequence that I wrote did heads, tails, tails appear. Okay, so they make these bets, and we're going to ask who we expect to win first. In this game here, player 2 won. And then more generally, we'll ask, what are the optimal strategies in this game, or is there one? Right? Maybe it's all just random chance. And so we are going to analyze this by looking at it as a Markov chain. And so what do we do here? We'll take, I'll take this one. So here's a Markov chain, and what I've done is I've said there are 8 possibilities, right? At any given iteration of this game, you look at the last three. You look at the last three outcomes, and there's 3 possibilities there. And so we look at how these transitions could happen. So I'm going to copy that chain that I just wrote before. I said, actually, I'll copy it one by one, and as I do that, I'll make it bigger. As I do that, I'll trace out the path along this Markov chain. So you started with, let's say, tails, tails, heads. That was your first. That was the first 3 things that you saw. And so you would start in this case at, where is tails, tails, heads? It's down here. Okay, you started here. And then what happened next? Then you saw tails, and then it was a tails. And so now you went from tails, tails, heads, now to tails, heads, tails, which means you went over here like this. And then what happened next? You went tails, tails, heads, tails, heads. And so now you're at heads, tails, heads, which means you go over here like this. And then what happened next? Tails, tails, heads, tails, heads, heads, like that. And now we're at tails, heads, heads, which is down here, this one. And then finally we hit heads, heads, tails, which is the final state at which point player 2 happened to win. And whereas heads, heads, tails is up here, like that. So that game that we just played involved this sequence of 1, 2, 3, 4 moves that you went on. Okay, so easy to see that this is a Markov chain. And I've written here all the probabilities are 1/2. Of course, every turn you get either a heads or a tails. So all the probabilities here have a 0.5, so we don't need to mess with that. Okay, so that's the chain for this game. Although in the chain I've drawn here, you'll notice I don't have any winners or losers identified, right? This chain here corresponds to what happens if you just keep playing this game forever. And so we have to adjust this chain to factor in the fact that either heads, tails, tails, or heads, heads, tails, either one of these means the game is over and you're finished, right? So what do we know? How do we model that when a game is finished and over? Well, you make absorbing states, right? And so what does it mean we need to do? We need to make absorbing states. Oh, I should make a remark here that before we do that, I'm getting ahead of myself. The first thing I should mention is that the very here we started at this location, tails, heads, tails, heads rather. We started down here because that was the first thing that we observed, and so we have to modify this chain a little bit to reflect where you're starting from. Okay, and it's easy to show that that you're equally likely to land on any of these 8 locations to start with, right? You're equally likely to land on any of those because the first 3 are just one of 8 possibilities. And so the way I like to represent this is I always like to add in an additional state, which I usually call state -1. And state -1 represents sort of before the game has even begun. And so you'd put in an additional state here. I'm putting in a -1, and I'm connecting it to all 8 possibilities like this with a probability of 1/8. And I like to do that just because then everything is represented in terms of a chain, and you can make all the conclusions you need from that. So that's how I would choose to model that. You can also do it using the alphas that we had before, where you have an even probability of, or an equal likelihood of landing in any of these states next. So you could do that too, but I happen to prefer this way. So we're going to add in one more state that reflects the before the game has even begun, and you're equally likely to land in any of these things, any of these states. Okay, so we've done that, and now I'll get back to the point I wanted to make, which involved how do I model the premise where someone wins when you land on either HTT or HHT. Okay, we want to know which of these is more likely to happen first, and in any event, the game is over. So how do we adjust the Markov chain to answer this? Well, what do we know? As I mentioned before, you're going to create absorbing states. So what will we do here? We'll take heads, tails, tails. That's player one's favored sequence, and then heads, heads, tails, that's player 2's sequence, and we'll make those absorbing states. So I've done that by making a little blue loop here, which has a probability of 1. So now we've changed the chain, we've adjusted the chain so that states 3 and 5, which are the winning moves for player 1 and player 2, so that those are now absorbing states. Okay, and now what do we need to do? Now all we have to compute is we say, well, if you start in this state, -1, which is, by definition where the game always starts, you then just ask, well, what is the probability that I ever land in state 3, and what is the probability that I ever land in state 5? You see, both of these are absorbing, so you can only land in one of them, and then the game is over. And so we're going to look at the 2 hitting probabilities of each of these. And depending on what those are, we'll conclude who the game is more favorable to. Okay, so once we've done that, we've got a nice system of equations, just as you've seen throughout. You'd solve things in the usual way with these hitting probabilities. So I'd say the hitting probability, we're gonna say, okay, H sub whatever, H sub I, will be the probability that I see HTT, okay, as opposed to heads, heads, tails, HHT. So HTT will be the one we're interested in here, this one, okay, and that'll be the probability that player HT is player 2. So here's the probability I think that player 2 wins. Okay, so H -1. Remember, you have a 1/8 probability of going to any of the other 8 states. And then H naught, which one is H naught? H naught is, naught is HHH. So where can you go from state 0? You go either back to state 0 or you go to state 3. And so you can see here H naught is equal to 1/2 times H naught plus H3, and so on and so forth. I would say H3 is equal to 0 because that's an absorbing state where you lose. Right, H3 here, this is the absorbing state where where you lose the game, and then state 5 is where you win the game, and therefore that would have a probability of 1. So you solve this system of equations, and what you work out here is that h sub minus 1 is 1/3, which means you have a 1/3 probability of hitting heads, tails, tails before you hit heads, heads, tails. Okay, so heads, heads, tails is twice as likely as heads, tails, tails. So the person that bids heads, heads, tails is more likely to win twice as often. Okay, which is kind of surprising already because I don't know, I would have thought all these sequences are more or less the same, but they are not. And here's something even more interesting. In fact, so what did we establish here? We said, okay, HHT beats HTT with 2-to-1 odds. Okay, so we'd say, all right, what would we conclude from that? We'd say, well, all right, HHT is better. So HHT is, I'll do it this way. HHT, I'm going to write it down like this. HHT, we're going to say that is better than, so I'll do a greater than sign for that, is greater than HTT, right, on average. Okay, but you could also do the same analysis to say that HTT is actually better than TTH. Okay, HTT is better than TTH. And I'm going up in with these bullets for no particular reason. HTT is better than TTH. And then I would say TTH is better than THH. THH. And then THH is better than HHT, which is kind of weird because we started with HHT. So this is what's called a non-transitive game because you have cycles there, right? It's kind of like rock, paper, scissors, but with a probabilistic element in there. So in fact, in this game, there isn't a best option. No matter what player 1 chooses as their pattern, let's say heads, tails, heads, player 2 can counter them with something that is more likely to win at least twice the time. And in fact, if they choose something really bad, then they would win 7 times as much. So let's look at one particular example here to see how this works, right? So this tells you that heads, heads, heads is really bad. All right, heads, heads, heads loses 7 times, 7-to-1. It loses to tails, heads, heads. And you could reason this out with a very rudimentary amount of probability. Right? Why is this? So if I have said heads, 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 okay, I claim that the only way I can win this is if the first 3 flips are heads, heads, heads. The only way I can win this is if that happens. What else? If there's ever a tails anywhere in those first 3 examples, heads, tails, let's see, heads, tails, heads, and then, I don't know, tails, heads, heads, that would be now a win for tails, heads, heads like that, right? Why does this work? It's because if I need heads, 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 but there exists a tails somewhere, then you're always going to get to tails, heads, heads before I get that additional heads that fills me in and wins it. Okay, so that's a quick sanity check why, choosing all the same thing is a really bad option to choose. And if you want to memorize this strategy, if you're doing a betting with a friend or something like that, the winning strategy is easy to remember that if your opponent does ABC, if ABC or whatever they choose, then you choose the opposite of B and then A and B. Okay, so what do I mean by this? If my opponent chooses HHT, all right, which would be A, B, and C, like that. And then this is telling me take the opposite of, so minus B, A, B would be the opposite of B, which is tails, and then A, which would be H, and then B, which would be H, like that. So tails, heads, heads beats heads, heads, tails, as we've seen here. Did I get that right? THH beats HHT. Yep, there it is. So that's Penny's wager. And you can do this with decks of cards, red and black, if you want. And it's a very counterintuitive result. Well, let's try something a little different now. What we've learned so far is here's how the probability, or here's how to compute the probability that you eventually land in a certain state, right? We call those hitting probabilities. It's the probability that you eventually win the gambler's ruin, you eventually lose, and so on and so forth. We haven't yet talked about how much time elapses before this event happens, right? You're also interested in saying, well, how long what's the expected amount of time until I either win or lose the gambler's ruin game. And for that, we introduce something called the hitting time. The hitting time, we say, is the minimum amount of time until you land in a given set, which we'll call A. Okay, so T is the minimum overall time steps that the state you're in belongs to the set A. Okay, A might be just one state. It might be the state of losing. It might be, multiple states. Like in that pennies wager, you could say maybe A is player 1 or player 2 winning, and we compute the hitting time until one of those occurs. So if the hitting probability is less than 1, that means that there is a positive probability that you might never come back to this state, or you might never come to this state. And when that happens, you'd say T is infinity, right? So T equals infinity does actually make sense in certain cases. It's how you would write that, well, this thing might never happen. So we're going to show how to compute the expected hitting time, or mean hitting time, expected value of T, and it follows in a really natural way from what we've already done. You apply all those same principles there. Let's start with this state here. So we got this chain rather. You got this chain, and we'll say we are interested in the amount of time until you land in state 4. So in this example here, state A would just be that one single state 4. And we'll say T0 through T4 is the vector of the expected amount of time until you land in that state. So we're going to say T4 is equal to 0 because you're already there. Now, a natural question is to say, well, what if I wanted to know if I'm already in state A, or in this case, state 4, the probability or the amount of time until I come back to this state, until I return to it, right? We'll look at that later. That's called the return time. But for now, we're going to use this convention where if you're already in the state, then that time is 0. Okay, so let's use the exact same principle as before to compute this expectation. Okay, what is T0, for example? So T0 is the expected amount of time if I am in state 0. It's the expected number of steps until I land in state 4. Okay, so how do you compute this? What's going to happen? Well, if I'm in T0, then what is for sure true? Well, at least one step has to elapse, right? At least one step has to happen because I'm not in state 4. So there's at least one. So it's 1 plus. And then what happens? What are the possibilities here? Well, there's a 0.4 probability that I go to state 1. All right, so there's a 0.4 probability that I would go to state 1, and then we'd want the expected time to land in state 4 if I start in state 1, so that would be 0.4 T1. And then what's the only other option here? 0.6 is the other possibility, and that's if I land in state 3, like this. So 0.4 T1 plus 0.6 T3, as I've done there. And how about T1? T1, you do this exact same kind of analysis, and you'd say, well, okay, if I'm in T1, or if I'm in state 1 rather, then there is a 0.1 probability here that I just go back to state 1. So T1 is equal to it's a 1 because you have to do one step there. 1 plus, and then there's a 0.1 probability that I just go back to T1, and then plus, what are the other options here? There's a 0.9 probability of going to T3. Like that, okay? And I think you can believe me, you could complete this system and just apply this same reasoning for all of these other states. So here's the system, okay? Here you could, if you're working through this asynchronously or whatever, you could look through and verify that you understand how these computations work. Throw this into Mathematica, Wolfram Alpha, MATLAB, whatever you want, and you get this thing here, okay? You get this vector. And so what does this say here? This is 6.32 is the first entry. That's T0, okay? That's if I'm in state 0, then the expected amount of time until I land in state 4 is 6.32 steps. Okay, and then 5.98 for T1, 7.75 for T2, 4.87 for state 3. Okay, so now we know how to do that. Now we know how to compute the expected amount of time until I land in state 4. And so in general, the theorem works like this, just what you've seen. You extend this example to any kind of chain. The vector of hitting times, as we said before, is the minimal non-negative solution to this system of equations here, which is just a formal way of expressing the equations that I had before. And again, this business about minimal non-negative just means make the entries as small as possible without being negative. So you'll sometimes see when you solve this in a, if you solve this in Wolfram Alpha or whatever it is, it might spit out some degrees of freedom and say, well, the solution system is underdetermined. And when that happens, you just take your free variables and bring them down. You can see examples of that in the future. So let's talk about that winning by 3 example again. This was that problem that was identical to the gambler's ruin, right? It's exactly that, except we decided to re-index all of our states just to make things a little more intuitive. So the problem again is that players A and B are playing a series of games, and A wins each game with probability P, and so B wins with probability 1 minus P. The overall winner is the first person who wins by 3. Okay, and before we computed the probability that A wins, which was the probability that we eventually land in this state over there. But now we'll ask, how long do we expect this game to take? Okay, and we're going to use this principle for that. So, of course, we will start in state 0 because eventually, or initially, the score is tied. And then we're going to ask, what is the expected amount of time until we land either in this state here, number 3, or in this state over there, minus 3. What's the expected amount of time until that happens? So what does this system look like? Actually, here, I'll write it out by hand first, and then you can see it looking all nice. We'll do, let's see, what did I start with on that one? T minus 3. Okay, well, we'll go from left to right. So T minus 3, of course, is 0 because the game is over. You're in state 3. That's fine. How about T minus 2? Well, what are the options here? T minus 2, there's a 1 minus P probability. Sorry, I keep making this mistake here. It should be a 1 plus, because you have to do at least one move. So it's 1 plus, and then there's a 1 minus P probability that you go to state minus 3, and then a P probability that you would move to the right and land like that in state minus 1. Okay, and that was ugly, so let's just do one more, but I'm sure you see the pattern here. T minus 1, you would look at state minus 1 here, and let's erase all my scratches. T minus 1, you'd be here, and you would say, okay, well, there's a 1 step that has to happen, and then plus, either you move to the left with probability 1 minus P, like that, 1 minus P times T minus 2 plus P times T minus 1. Okay, and you could, I think it's probably pretty clear that you could continue this line of reasoning for all of those, right? I've written the system here, and it's a really easy one. So you work it out. Again, you could throw this into Wolfram Alpha or whatever, and what we were interested in here is we're interested in T naught, right? Because we're starting in state 0 because no one has won or lost anything yet. So we're interested in T naught, and you can solve this as a function of P, and you get this expression over here. Okay, so what does that look like? Here's a plot of that thing as P varies. So as P goes from 0 to 1, the T naught looks like this, and we can get rid of all probabilities 1/2. That doesn't mean anything there, of course. So not surprisingly here, when P is equal to 1/2, you have the longest expected time to get to a winning state for someone, because it's an even game, so you bounce back and forth a lot. And then also not surprisingly, you approach 3 at the limits, because it's more likely that the first person is just going to win or one of the two players is just going to win 3 games in a row. We can apply this kind of reasoning to Penny's wager. What is the expected amount of time until we see, for example, heads, heads, tails, this system over here? So we'll start in that state -1, as I mentioned before, and we'll apply the same line of reasoning here. The system of equations, which I won't even bother writing out because I think you can follow along, look like what you see here. Oh, no, I will make one comment, which is that I have a 3 here for the state -1, which is a silly sort of idiomatic convention that I'm doing just for this problem. And so I'll explain that, but first I just want to point out where that's, well, I'll set the context here appropriately, which is like this. So as I said before, we are interested in the amount of time, the expected amount of steps that have to elapse before you see heads, heads, tails, which is state number 3. And so T3, of course, is 0. And for all these other states, other than, weirdo -1, you have the same expression we're used to, which is that it's a 1 plus and then the weighted sum of the other hitting times for the other ones here. Now, for this particular game, I decided that for T-1, I would put a 3 here. And that 3 corresponds to the fact that in the very first iteration of the game, or when you first start the game, you have to flip the coin 3 times, right? Because you have to flip 3 to get, a sequence of 3, heads, tails, heads, or whatever it is. So I decided to put that in that way. If you were on an exam and you wrote a 1 in there, it would be completely fine. I mean, there's nothing wrong with that. It depends on what you consider to be the number of turns. So I put a little 3 there and an exclamation mark just to sort of emphasize that if you're talking to someone and how many turns would have to take to get to this particular state, right? It would have to be at least 3 because you have to flip the coin 3 times, and then anything that happens after that is in addition to that. So that's where that 3 comes from. But don't worry about that. That's just because of the particular way I've decided to set this system up. I also should point out that you can actually answer that same question in a much easier way by simplifying the chain. So let me go back to that, right? This is a pretty big chain. It has 9 states in it and, I don't know, a good number of edges, right? And so drawing that thing and working everything out is kind of nasty. But if you just want to focus on how likely you are to see heads, heads, tails, you can actually simplify things a bit, okay? So we're going to ask, what is the expected amount of time until I see heads, heads, tails? You can actually answer that question using a much smaller chain, and it works like this. You can do this with a chain that has only 4 states in it, and where do these come from? So we'll start with, what we're going to do, rather, is we're going to have the state just record how much progress we have made towards heads, heads, tails. So either you've made some amount of progress towards heads, heads, tails, or you've accomplished nothing. All right, so how does this work? So initially you have made no progress, so you're in state 0. And then what happens? How could you make progress in this? You could flip heads, right? You're looking for heads, heads, tails. So if you flip a heads, you're happy because you've made it a third of the way. Right, so then what I would do is I'll write, okay, state number 1, I'll say that's when you flip the heads, and there's a 1/2 probability of that happening. And on the other hand, if you flip tails to start, you would just get 1/2 here like that, right? You'd have made no progress, and so nothing changes. And then you'd say, okay, suppose I've just flipped the heads, and then I want to flip another heads, right? So there's a 1/2 probability. In fact, all of these arrows are going to have 1/2s on them, but we'll write it this way anyhow. So there's a 1/2 probability that I gather up an extra heads like that. And on the other hand, there's a 1/2 probability that I get tails, which resets my system and puts me back where I started like that. So 1/2 probability that I go back to 0, because if I flip a heads and then a tails, then I've reset myself. And that resetting concept is what's key to all of this. So 2, now let's say you're in state 2. Now this is kind of an interesting one, because what could happen? when you're in state 2, what are the two outcomes here? You could either flip a heads or a tails. Let's look at the easier one first. If I flip tails, then I've won the game because I flipped heads, heads, tails, and that'll be state 3. And since I've won the game, I'm asking, the expected amount of time until you see that. You would have an absorbing state there, right? The probability 1 of going around. But now let's ask this. Let's suppose I'm in state 2, heads, heads, and then I flip another heads, right? What happens at that point? If I see heads again, then I actually stay in that same state. Because if I've just seen heads and heads, and then I flip a coin and I see heads again, I'd say, well, nothing has changed. I haven't made any progress to the right because I'm looking for a tails, but I haven't moved backwards because I've just maintained this pattern of a bunch of heads. And so I'd have a 1/2 probability of staying there. So in this particular game, you're really happy once you've seen heads, heads, because you know that you're never going to reset the chain at all. So that's a simpler way of analyzing this system. And you can work that out, and you'd see that the expected amount of time is eight turns until you see that particular pattern. So that's how that works. I said earlier that we would also look at the expected amount of time until you return to a particular state. Right? That's the one where you're in a state and you want to know how much time is it going to be until I come back here. So that's different from hitting times, as I previously mentioned. And actually, this is a really easy algebraic calculation. All you have to do for this is compute the hitting times, and then just set the return time from a particular state to be 1 plus the sum of all the outgoing edges of the edge probabilities of Pij times Tj. Okay, so just look at all the hitting times to that state and the probabilities of transitioning into those states there. So that's easy. If I ask you about the time to return someplace instead of just the hitting time, you can compute it in one expression by computing the hitting times and then evaluating this sum. Here's another idea. You could have general utility functions, right? Instead of asking about the amount of time, the expected amount of time until you land in a particular state, you could say it's at every one of these states in the chain, maybe there's some kind of reward that you accumulate. Okay, you get paid for being in these various states, and maybe that payment is negative somewhere. That's fine too, right? We can just talk about what happens to some general sense of utility as you move throughout this chain. And let's do Wheel of Fortune as an easy example of this. Right. The way Wheel of Fortune works is you're spinning a wheel and you make various amounts of money. But then as soon as you hit that bankrupt state there, then not only do you lose all your money, but the game is over too, so you're done. So the strategy of the game is that you want to play to make some money, but once you make enough, you're going to say, okay, I'm going to play it safe here, and I'm going to take what I have because I don't want to run the risk of going bankrupt and losing everything. And so we'll model this with a really simple version of this where you have just a very boring wheel with 5 equally likely states. And we'll say state 0 means you go bankrupt and the game is over. And then states 1 through 4 have a reward of $15, $5, $20, and $2 respectively. And we're going to ask the question of the expected amount of money you will have right before you go bankrupt, right? We want to know, on the average, how much do you make before this game ends and you lose everything? So we can model this as a very uninteresting Markov chain here, and it's really uninteresting because all of the transition probabilities are just going to be 1/5 because you're not any more particularly likely to go from one state to another. Right, it's always just a 1 in 5 chance, so it's not a very interesting Markov chain. The matrix just has a bunch of 1/5s in it everywhere. I guess the one exception is that the bankrupt state is absorbing because once you're bankrupt, you're done and you have nothing. So the chain is just what you'd expect it to be. All these black probabilities here are 1/5, and then this blue probability here is 1. The chain looks like that. It's not very interesting. And so how do I compute the, we'll do the utility in a minute. But the first thing is I'll do my same little trick of introducing a starting state. which I'll call -1 again, representing the beginning of the game when nothing has happened. And I would say that there's a 1/5 probability of going to any of these states too. And I've given them a different color just to emphasize that this state is artificial or different somehow. Okay, so I've done that. And how do these utility functions work? We'll say R sub I is the expected amount of money that you will make if you start in state I. Okay, and we are interested in R sub -1 because you're beginning in state -1. And the equations look like this, right? If I start at -1, then what is the expected amount of money that I will end the game with? Well, there's a 1 in 5 chance of going to each of the other 5 states. So it's 1/5 times the sum of the other possibilities. R0 is 0 because if you're bankrupt, you're not going to make any more money. R1, you'd say, well, if I'm in state 1, then I've made $15. And then the remaining amount is just 1/5 times the sum of these other return values here. Okay, and in fact, because you have this property of the Markov chain that the states or the transitions are all just 1/5 everywhere, you'll see all of these rewards just have a 1/5 times the sum of these rewards, which is not very interesting. And the only thing that distinguishes them is that you have either a 15 or for R2, it's a 5 because you've made $5 in state number 2. If we look back at that wheel there, right, state number 2 has a $5 attached to it. So if you start with $5, then, or if you start in state 2, then you would have $5 and so on and so forth for R3 and R4. And so you run this, you solve this system, and you find that the vector looks like this. So R sub -1 is 42. Of course, R0 is 0. And then the other possibilities here, 57, 47, 62, and 44, depending on these other states that you start in. All right, so what does this say? This tells me when I begin that game that on the average, right before I go bankrupt, I will probably have $42. On the average, that's how much I will have. And so if I'm playing this game, a common sense strategy would be that I would play the game, and then as soon as I get to 42 or greater, I should probably quit while I'm ahead and say, well, okay, I've made about the average amount that I expect to, so I'm doing relatively well, and it's a sensible time to stop.